Hi guys, welcome to Basic Differential Equations. This is lesson number 5 in our unit. So what are differential equations? Well, these are equations that contain a derivative, okay? And I'm going to use capital DE to abbreviate differential equations, okay? So these are equations that have a derivative in it, and solving it means you are working backwards and we're looking to find the original function. Well, if we're going to go from a derivative to an original function, we're going to need the antiderivative. So we're going to have to find the integral of what's given in order to solve it. Just some lingo here. If we're talking about a first order differential equation, that's where you're given the first derivative. If we're told that we have a second order differential equation, that would imply that we're given the second derivative. But the majority of the time we're going to be looking at first order differential equations. So here's a quick example. Suppose we're looking to solve the differential equation dy dx equals, and you see that expression right there. Well, we've already studied our rules of integration. All right, if we're going to work backwards here, we just need to integrate this. So if we work backwards, we're going to end up with a y equals equation, or we can call it f of x, but since we see dy dx, we'll write it as y equals, okay? So we know if we were to integrate this, we would have tangent of x, right? That's the integral of secant squared. This 2x would become x squared, right? Those 2's would cancel out. Then you'd have a plus 5x and then a plus c. Now, this is known as the general solution. Let's write this down. This is our general solution. It's general because of that plus c, as opposed to a particular or a unique solution. In order to get that, we would need additional information to help us pinpoint what c is. So because we have that generic c, we call it a general solution to this differential equation. And again, what makes this a differential equation is the fact that we were given a derivative, and it's a first order differential equation because it's a first derivative. All right, so let's take it a step further. Suppose we want to find a particular or a unique solution. Well, if this is the case, we would need to be given what we call an initial condition, all right, which is a value of the function at a single point. And the function we are referring to is the solution curve, or f of x, okay? So here's an example. Suppose we want to find the particular solution to this equation. We see dy dx, so it's a differential equation, equals e to the x minus 6x squared. So again, we're looking to work backwards here to go from the derivative to the original equation. And we're told that this graph passes through the point 1, 0. Now this 1, 0 is on f of x, not the derivative, but the original function. Okay, that's how you interpret that. So let's get the original function, all right? So let's call it f of x, or you could call it y equals, it doesn't matter. So let's integrate these two parts. So we integrate e to the x, e for easy, same thing back, and then minus, well, this would become an x to the third. We would be dividing by that 3, which is going to turn that 6 into a 2. Okay, so e to the x minus 2x cubed is what we're looking at, and then a plus c. Okay, now this is our general solution. To find the particular solution, we're going to use this point of 1, 0 that we're given. Well, of course, that means we're given an x and a y value. So at this point, you're going to plug in 0 for the y, and you're going to plug in 1 for the x. And then you're going to solve for c. All right, so do this very carefully. We have e minus 2, and then plus c. So if I solve for c, I would have to add over my 2 and subtract over my e. So c is whatever 2 minus e is. Okay? So let's suppose we're not using a calculator here. Exact is always preferred. So here's our c value. So now my final answer here for my function, f of x equals, I'm going to go back and copy down what I have from earlier, except this time we know what c is. It is the number 2 minus e. So we just tack that on to the end like that, and this is our final answer. So this is our solution to the differential equation that passes through that point. Bye-bye. Sorry, that was a premature bye-bye. We have a little more to do here. So sometimes it's not going to be possible to algebraically find an antiderivative. Okay, so we don't have rules for everything. We can only go so far. So we're done with all of our techniques of finding antiderivatives. So at this point, if we don't have a rule for it, we assume that we can't do it algebraically, at least not in this course. So recall that we can find a solution using the fundamental theorem of calculus and accumulation functions. This is from last unit. So what the heck am I talking about? Well, suppose we wish to find the solution to this differential equation. It's a differential equation because we see a derivative, f prime of x. We have e to the negative x squared. So again, we don't know how to integrate this because we're missing an x term next to it. It's not just e for easy, get the same thing back, right? Because we're missing the derivative of that inner function, right? There's no x there anywhere, so we can't make it show up. So we don't know how to integrate that. We are told that f of 7 equals 3. So to find f of x, we know that an antiderivative will wipe out a derivative. So to get f, I can just take the antiderivative of f prime. So if we do that, recall this is where we said we're going to take the x value and make it our lower bound, and then we're going to put an x up here as our upper bound. And then I'm going to rewrite the function, but I'm going to change the variable. Let's say we change it to t. Okay? So if we were to find the antiderivative of this derivative, remember this is really our derivative inside here, okay? If we were to do that, that x would fall into where that t is, okay? And so that would give us, if we were to put this into it, the integral from 7 to 7, well, that's going to give us 0, right? The area there would be 0. And then we know the y value is 3, so I would have to tack on a 3 here, okay? So if I were to check this by doing f of 7 would give me 3, because again, this integral piece here would just be 0, okay? So why do we need a t like that? Well, it's because when we apply this antiderivative and we take its derivative, the x gets dropped in to where the t is, all right, so it becomes f prime of x, okay, so it would match what we're given up above if we took the derivative of each side, okay? Okay, let's take it one step further. Suppose we're allowed to use a calculator and we're asked to find f of negative 2. So f of negative 2 would mean we're going to drop in a negative 2 where we see an x, well the upper bound is x, and then we still have this e to the negative t squared dt and then plus 3. Okay, so we're going to use the calculator to do all the work for us. Notice how the bounds, you have actually the bigger bound in the bottom, the smaller one up top. Doesn't matter. It would matter if we were doing it algebraically by hand, but we're just going to let the calculator handle all of this. So if we were to do fn int on that and then add on 3 to that answer, all right, you would end up getting 1.23, and it would be a 2 if you round, okay? So you want to certainly check that on your own. Don't just take my word for it, okay? So we're using the result to find f of negative 2.